think anyone will be too worried about missing the rant on physics, but they might be, you're right, worried about missing the mathematics. Okay, so there was a result that I actually wanted to hit last time that I forgot to, and we're actually going to need it today. So why don't I start with that one? I think we can call this a theorem. I think that's fair. So I'm going to start to be just a little bit lazy in the sense that I'm not going to say what the domain and codomain of the function are, just because it's a pain. You know that it maps into the real numbers. You know that its domain is maybe some interval of R. So I'm just going to say if f is a function which is differentiable at C or something, right? So let me write exactly that. So if f is differentiable at C, okay, so again, I've been sloppy. I haven't said what the domain and codomain are. Normally you would, but I think we understand what's going on here, right? F is defined in a neighborhood in like some interval or something containing C. Then f is continuous at C, okay? So this says, I'm writing a little bit up the screen, but this says that differentiability implies continuity, okay? Now the converse obviously is not true. And if you haven't thought about this before, I suggest that you do try and think of a counterexample. But let me say, right here, let me do the proof of this, and then maybe we can talk about this a little bit more. So we want to show f is continuous. That means, so not only does the limit exist though, right? So we need the limit to exist, but we also need that the limit of f of x is equal to f of c, right? So we need that very specific thing. So we need to show that the limit as x approaches c, f of x equals f of c, right? Now that's equivalent. This is equivalent to showing this, and hopefully it'll be clear in a second why we're going to show this instead. F of x minus f of c equals 0, right? Now, I think that many of you probably agree, like, oh yeah, okay, that makes sense. I can see that basically what I want to do is move the limit or move the f of c onto the left-hand side and throw a limit into it. That's sort of the intuition. Strictly speaking, if you actually want to prove they're equivalent, you want to do it in a slightly different way, right? The way you would actually do it to make sure that you don't, run afoul of the limit laws is you'd say something like this. So assume that we know that f of x minus f of c goes to 0. Right? You would say f of x minus f of c plus f of c like that. Now we do know the limit laws, so we know by assumption that f of x minus f of c goes to 0, and the limit of the constant function always exists. So we can limit law this. Right? And this thing here, that's 0. This thing, that's just the constant function, so that's f of c. So this whole thing is equal to f of c, right? And that is what we wanted to show. So if you kind of ignore all the stuff in the middle, here, let me maybe try and tighten this up a little bit. F of c, like that, okay? So if you ignore all the stuff in the middle, yeah, that's what we've shown, right? And we've shown the limit of f of x is equal to f of c. And again, you might say like, well, why did we do this? Why didn't we just move the c to the left of the equals sign? You can try that. The problem is getting everything to work out with the limit laws, right? Because generally, for example, even if I took this assumption that limit of f of x minus f of c equals 0, I'm going to have a little bit of trouble arguing that the limit of f of x exists, and therefore that I can use the limit law to split this up. If I can do that, great, but I don't actually know that, right? So this is how we would kind of do it to get around that. So anyway, it doesn't matter as long as you can convince yourself that that's the thing that we want to show. Okay, so we want to show a limit of f of x minus f of c is 0. And now hopefully you see like, oh, hey, like that's the numerator of the difference quotient for the derivative, right? So great. So thus, let's take the limit of this thing. Let's start computing what it is. And now the trick here, so in the green stuff above, I added and subtracted f of c. I'm going to do something similar here, except I'm going to multiply and divide by x minus c, right? And again, that's totally okay, because remember, generally when you take a limit, you're saying, yeah, I don't care about what actually happens at 0, right? And so I'm not multiplying and dividing by 0 here because x is not equal to c. Okay, so now I know I can split this up because both limits definitely exist. Right, because I was told that f was differentiable at c. That's why I'm allowed to split this up. If you don't know that the function is differentiable, you can't use the limit laws here, right? And now we can evaluate that's f prime of c. This thing is 0. And so we get 0. And again, if you kind of ignore all the middle stuff, we've proven exactly what we wanted to prove, right? We showed that the limit of f of x minus f of c is 0. So our function is continuous. All right. And there we go. And really, again, you can kind of do this proof without the green thing, right? So you can skip the whole green stuff as long as you're convinced that, yeah, that what we're trying to show is equivalent to continuity. In which case, the proof is actually quite short. Okay, so all differentiable functions, right? Let's think about what this theorem says. This theorem says differentiable functions are continuous, period. Really, it's at every point, but obviously we can extend this to the entire domain. If your function is differentiable, then it's also continuous. Again, the converse is not true, okay? The classic converse is the absolute value function. Right, so this function, we know this function is everywhere continuous. I think I made you do it as like an exercise. Now, the really critical point is going to be at 0, right? Because we know if you graph this thing, it looks like a V. So it's got this little corner at 0. So f of x equals the absolute value of x. This is continuous at 0, but not differentiable there, right? So it shows you that the converse is not true. This is not an if and only if. Okay, but not differentiable at 0. Okay, so we can use a limit law if we know it is differentiable, even if we don't know the limit exists. Well, no, we do, but okay, so here's what I'm saying. So we don't know necessarily the limit of f of x exists, but we do know that this exists. And because this is exactly the derivative, right? Since f is differentiable at c, we're told that f is differentiable at c. And the definition of f being differentiable at c is that that limit exists, right? That's why we were able to split it up. So does that make sense, Kevin? So I'm not saying that like we somehow magically use the limit law there. It was the fact that we knew that that difference quotient limit existed ahead of time, because that is what differentiable means. So we were able to use that and leverage that in order to be able to split it up with our limit laws. Yeah. Did I assume that f of x equals f of c and use it to prove that f? So where do you think I assumed f of x was equal to f of c? Let's see if you can point that out to me. Because I don't think I used it. Yeah.
I think I better unmute myself. Like the right side of the equation, the green words.
Mm-hmm. Like
you said. Limit of fx minus fc equals to 0.
No, we assume that. So what I'm trying to show is that if this limit is 0, then f is continuous. Right? So knowing that that limit is 0 really isn't an assumption that f of x equals f of c, right? I'm just saying, assume this limit is 0. Who knows what that implies about f? And in fact, at the end of the day, we're not really worried about what it implies about f. I'm just trying to show that if we can prove that the limit of that thing in brackets is 0, then that is the same thing as having proven that the limit of f of x equals f of c. So the green stuff is the proof that the yellow statement is true. Right? And so where I use that is right here in this equal sign, so that I can apply the limit laws and split this limit up into its two parts, right? Because I need those limits to exist. And by assumption, the limit of f of x minus f of c does exist. And the limit of the constant function, just f of c, certainly exists. So I can just split it up like that. So in order to use that limit law, I needed to know that limit existed in the first place. Is that okay then? Does that make sense?
So the green part is used to prove that the limit exists.
To prove the continuous. Like if you know this, then your function is continuous. Right? And that's what the green is proving. Yeah.
Can I see the original question?
Sure. Like what the theorem statement is, you mean?
Oh, okay.
Yeah. So what the green is saying is, I don't want to try and directly prove that f of x goes to f of c, right? I don't want to prove that because that's kind of hard to work with. So what I want to do instead is to prove that f of x minus f of c goes to 0. But I have to justify why I'm allowed to do that, why it suffices to prove that result instead. And that's what the green thing is doing. It's justifying why I can prove this other thing instead of directly proving that f of x goes to f of c. Okay, good. Okay, I will assume so. All right, so the absolute value x is continuous at 0, but it's not differentiable there. And okay, continuity we already know. So we already know about continuity. And then if you do differentiability, so what I'm going to do is I'm going to break this down into computing the limits from the left and right. Right? Because we know that the two-sided limit exists if and only if both of the one-sided limits exist. Well, f of 0 is 0. So this is going to become the absolute value of x divided by x, and that's 1. And you can see what's going to happen, right? I think that we've talked about this limit before. Minus f of 0 divided by x. So we get the same limit. But if I approach from the left, the absolute value of x becomes negative x, right? So I get negative x divided by x, that gives me negative 1. And since these aren't equal, that tells us that f prime of 0 does not exist. Right? And that has to exist in order for our function to be differentiable. That is the definition of differentiability. Okay, so this is an example of a function which is continuous, in fact, everywhere, but in particular, in our case, continuous at 0, but not differentiable at 0. Right? And exactly the precise reason why this fails is it has this corner here. This corner, as you can see from these limit computations, this corner simultaneously wants to have a derivative of +1, kind of corresponding to that right-hand side. Right? So it wants to have a derivative of +1 because of the line that shoots off to the right, but it also wants to have a derivative of -1 because of the arrow that shoots off to the left. So at 0, it's trying to reconcile both of those things at the same time. It's trying to have a derivative of both plus and -1. And of course, it can't do that, right? And so that's why it's not differentiable. So these corners tend to be failures of differentiability. There's another way that things can fail to be differentiable, namely if they get like a cusp. So cusps also lead to failures of differentiability. So those tend to happen when the limit is equal to infinity. So it doesn't exist still, but it tends to be equal to infinity. Really, what is kind of being said here is that differentiability is a smoothness criterion. Okay, so what that means is that you are differentiable at your point if in some sense you're relatively smooth, like you might change very quickly or something like that, but you don't have any corners, you don't have any cusps, you don't have any discontinuities, you don't have any of those things that can go wrong. So we'll often talk about smooth functions, and there is implicitly a differentiability condition when we say those things. Okay, and I haven't talked about C1 functions yet. We will eventually, but C1 is kind of the classical definition of smooth. Does anyone know what C1 means? Just out of curiosity, has anyone heard it? Actually, I guess I could just define it for you now. Do I want to? Right. Okay, so Yvonne, very close. I guess I could just define it for you now. So definition, so a function f, let's give this one actually needs a domain. F from D to R is said to be C1 on D if f is differentiable. And hopefully you can tell from the cadence of my voice, there's more coming. And f prime is continuous. Okay, so you not only require that the derivative exists, but that your derivative is continuous. And I think that for most of you, you probably can't think of an example. Maybe you can, in which case it would be awesome. So yeah, let's do this as a little exercise. I want you to try and think of, and I'm not going to give you the answer yet because we actually don't have the tools yet. But I want you to try and think of a function which is differentiable, but its derivative is actually not everywhere continuous, right? So it has a discontinuity somewhere. So this is a fun little exercise. It ends up to be a little bit tricky, but the function is elementary. Okay, the function is something that you've seen before, like you've seen all the parts of it. You just have to put them together in a clever way. The reason why we're not going to do this example yet is because I haven't shown you how to compute the derivative of one of the functions that you need. Okay, but if you've taken like calculus before, you know what the derivative of, so that, let me say this, there are classic examples. The classic examples involve sine and cosine. I haven't told you what the derivative of sine and cosine are yet, so I can't show you that example. But if you know what the derivative of sine and cosine are, usually most people use those in order to try and construct counterexamples. It will also help if you have the chain rule. So, and we haven't done any of those things yet, right? So anyway, the point of this, and I will define this again later. So if you don't understand what C1 means quite yet, once we finish the chain rule, I'll come back to it. But basically, this is, we often call C1 functions smooth functions. And they're smooth in the sense that, well, because they're everywhere differentiable, they actually don't have any cusps or corners. And the fact that we require f prime to be continuous is just so that we can do powerful things with it. There's a sense in which all you need is differentiable. You don't even need C1. But we usually just require C1 because we want to be able to do stronger things with them. Okay, and then C infinity are infinitely differentiable functions. Okay, so let's see if we can grind out product and quotient rules before we finish the class. And then that way I can just focus next week on the chain rule and the inverse function theorem, because those are our big theorems. So theorem if, and again, I'm going to be a little bit sloppy here just in the domains of the function. But again, it really doesn't matter. So if f and g are differentiable at a point C, then their product f times g is differentiable at C. And this is really the defining characteristic of derivatives. Okay, it's hard to explain because we need at least Taylor polynomials for me to really expound on this point. But it's very interesting, especially as you go up and do like integration by parts. And when you start to generalize the notion of derivatives into higher spaces, this is the defining characteristic of what it means to be a derivative. F prime, so like the derivative of f, did I screw that up somewhere? Right, it's the derivative of f, right? So it's the derivative of f times g plus the derivative plus f times the derivative of g. right? And even in my brain, that's still like I say that every time I do the product rule to this day, right? And I've known calculus for a bajillion years. I still say, the derivative of f times g is the derivative of f times g plus f times the derivative of g, right? As like my brain mnemonic, I still say that to this day. Okay, and the proof of this really isn't that hard. Okay, and it's going to be, would it be okay if we use dy dx? So it is okay as long as you say ahead of time, like, what do you want to say? So you'd have to say something like, if you want to put this into Leibniz notation, you'd have to say like, let y be f of x, and I don't know, let's say z be g of x, then dyz dx is dy dx z plus y dz dx. You could definitely say that if you wanted to. But you can see like it involves introducing a little bit more notation, right? Because you have to say like, what is y, what is z, like what are these things? You don't want to just make an assumption that y is equal to the product or y is equal to f or whatever the case is. But yeah, if you say that, and it's nice because it gives us an opportunity to write this down into Leibniz notation and see what it's saying. I don't think there's necessarily anything profound going on in Leibniz notation. Not like when we do the chain rule, we'll see something cool happen. But yeah, I mean, like this is a nice little exercise of us having written this down into Leibniz notation, and now we can see what it looks like. So yeah, as long as you define those variables, it's fine. Nope, won't be included tomorrow. The cutoff was Friday for test material. Okay, so this one's to use dy. I'm not certain what you mean by that, Rui. Can you expand? Yeah, don't treat dy dx as a fraction, right? Don't do that. There will be hell. I will come. Yeah, I will drop the fires of or the math hammer on you if you ever do that. This is not a physics class. In fact, we take a lot of pride in the fact that we do everything very rigorously in this class, right? So we're not going to allow ourselves some of that non-rigorous stuff. Is that true though? I feel like there might be a couple points in the class where I like do some non-rigorous things, but I will tell you when we're doing them, right? I will put up like a big sign and I will say, warning, not rigorous time. Okay, so the trick here is to do the same thing that we did. You remember when we were proving the limit law for products? And again, this is a common trick, and I tried to say so at the time, and hopefully it made sense. What I'm going to do is I'm going to do these cross terms, right? So I know that f goes with f of c and g goes with g of c, right? Like, because I know both of those functions are differentiable, f obviously pairs with f of c and g pairs with g of c. So in order to deal with this product and be able to split them, I'm going to introduce a cross term. So I'm going to use f of x and g of c. Of course, you could have used the other one as well. So if you wanted to use g of x and f of c, you could have. It wouldn't have made a big difference. And the benefit of doing this is that I'm going to be able to, look, I can factor, here, let me put this in big thing of brackets so we know we're taking the limit of the whole thing. I haven't applied any limit laws yet. Like that. Right? Okay, so what I've done there is I've factored the f of x out of those first two terms. And then instead of like keeping everything over x minus c, I kind of like pulled the f of x out of that, but that's fine because we know that that's how multiplication works. And now the claim here is all of these limits exist, right? So this exists, these exist because our functions are differentiable, right? F and g are differentiable. Y, okay, g of c we don't care about, right? This is a constant, so we know we can pull it out. Why does this limit exist? Right, so why does f of x exist as x approaches c? Why do I know it exists? Exactly. Yep. Differentiability implies continuity. If your function is continuous, what does that mean? Your limit exists, and more importantly, it's actually equal to f of c, right? So f is continuous. Perfect. So all the limits here exist, and because all the limits here exist, I can just super split this up. But I mean, if you're looking ahead, you already know what's going to happen, right? Basically, we're going to get exactly the formula that we need. G of x minus g of c for x minus c. Lots of writing. Okay, I don't need to limit this. This is just a scalar, right? So I can just pull that right out. And then we get the derivative of f out in here. And then if I evaluate all these limits, well, that's exactly what I wanted, albeit I think written in a slightly different order. F prime of x g of c. And so again, we've kind of done this differentiability and what the derivative is at the same time. We've proven that this limit exists and what it is. And so we're done, right? So thus, fg is differentiable. Okay. And so you can see, like, that's actually, again, I probably did more steps than were necessary because I really wanted to show you that I was invoking the limit law and that I was doing it in a completely legal way. But otherwise, the proof isn't hard. The only kind of trick is, again, introducing those cross terms. And the hope is that you are starting to recognize that, yeah, anytime you're dealing with a product like that, that is the right trick to do, right? Introduce those cross terms in order to make things work out. Okay, so are there, I guess I should say, are there any questions about this before I move on?
Professor, do you mind just explaining why it's FC G prime C plus F prime X G C? And
oh, you're right. That
no
should be a C.
Thank
yeah,
you.
That should be a C. Thank you. I just use my white. Yeah, absolutely. Should be F prime C. Thank you. Okay. So let's do a very quick example. We're not going to do a lot of computation, but I figured I should do at least one. Right. So I'm just going to say, I'm going to be really sloppy now about domains and such, and just be like, yeah, let's do this thing. All right. So let's find the derivative of this. And I mean, I guess what I'm using here implicitly is, even though the top formula talks about being differentiable at a point, we know then that we can use this formula in order to figure out the derivative function of f times g, right? So that's a nice benefit as well. So even though this theorem, right, is talking about f and g being differentiable at c, if f and g are both differentiable on their domains and their domains agree, then this formula says that f times g is differentiable also everywhere on its domain, and that this formula still holds, right? So often what we do, the most kind of widely used application of this is to actually compute derivatives, not necessarily to say that f times g is differentiable, but rather to compute derivatives. So let's just do that as an example. I mean, what we could do is we could say, note that this function is differentiable anywhere where both f and g are differentiable. Or let's maybe say, let's write this as a product of two functions. So let's say let f of x be x squared plus x plus 1, and g of x be 1 over x squared. Okay, so I chose this because we've played with 1 over x squared before, right? So we know what its derivative is. And we also know how to differentiate polynomials because we did the power rule and the linearity rule just the other day. So this is -2 over x cubed. Right? And so one thing that we can immediately do is we can immediately say, well, this function, f compose g, or sorry, f times g, plus 1 over x squared, is therefore differentiable whenever x is not 0. Right? Because f is everywhere differentiable. G is only not differentiable at 0. Right? And so by contrapositive of the theorem that we just did, the only way the product is not differentiable is if one of f or g is not differentiable at that point. The only point which is bad for either f or g is when x is equal to 0. So this function is differentiable anywhere where x is not 0, and its derivative is going to be f prime x g of x plus f of x g prime of x. And we just computed what all those are, so let's plug them in. So we're going to get 2x plus 1 over x squared. And then f of x g prime of x, this is going to be what? Minus 2x squared plus x plus 1 all over x cubed. And yeah, I think we should do some simplification here. So 2x squared plus x minus 2x squared minus 2x minus 2 all over x cubed. What are we going to get? Negative x minus 2 over x cubed, like that. Voila. Okay, so we always choose the smaller domain. I mean, yeah, as a general rule, if you know that f prime has a some domain and g prime has some domain, I mean, again, so this is a little bit sloppy. What you would really do here is you would really say, like, look, in order for me to even be able to multiply f and g, they implicitly have to have the same domain. And one way you can get around that is either demand that they have the same domain to begin with, or just take the intersection of their two domains and say that their two domains is now the domain of the product, right? So that's how you could get away with that. And then when you take a look at their derivative will also be the intersection of the domains of their two of the component functions, right? So if you take where f is differentiable and you take where g is differentiable, then fg will be differentiable on the intersection of those two domains, right? Precisely where both functions are differentiable, because you need both functions to be differentiable to talk about fg being differentiable. So if you want to think about it like that, you can. But yeah, if we have time, we'll do quotient rule. But yeah, I don't think you, Stephen, you necessarily don't want to say smaller because you don't even know that they'll be compatible, right? Like, what if f fails to be differentiable at 0 and g prime fails to be differentiable at 1, but otherwise they're both differentiable? Which of those domains is smaller? Neither of them, right? They're just incomparable, but their product will be differentiable everywhere where x is not 0 and y is not 0. Right? So that's why you take the intersections of their domains rather than looking for which domain is smaller. Just intersect the domains. If one is included in the other, if one is actually smaller, then the intersection will take care of that as well. Okay, that's good. Yeah, exactly. It'll give the same result. Yeah. Okay, cool. All right, so straight into, so that was the product rule. That's what that was called. I don't know if I actually wrote that down. So the next thing we're going to do is what I call the reciprocal rule. Okay, and it says if G is differentiable at a point C and G of C is not 0, then 1 over G is differentiable. All right, and that's why we need G of C to not be equal to 0. Then 1 over G is differentiable at C, and its derivative is negative G prime of C over G of C all squared, like that, okay? And I want to just figure out what the derivative of 1 over a function is, because then I can do any quotient by basically doing the product rule with this, right? So if I want to be able to look at the quotient f over g, then all I have to do is do the product rule with f and 1 over g, right? And that's where our quotient rule will come from. Okay, so again, this one isn't too hard to prove. You just kind of go through it. right? So 1 over g prime of c. And I think in my book, I maybe used the other definition of the derivative to do this. So that's a nice little exercise. If you guys want to like try and do this proof on your own, I'm using the f of x minus f of c divided by x minus c definition, but try the other one, right? The limit as h goes to 0 definition. See if you can make that one work. You definitely can, right? Because they're equivalent definitions. So we get g of c, g of x divided by x minus c like that, right? So I give everything a common denominators, and then I just combined the two denominators because you can do that. And again, we can kind of immediately see the derivative of g showing up, right? It's kind of like written negative. It's the negative derivative of g here, but that's okay because that's actually what we're supposed to get. So I'm going to immediately split this up. I'm going to do 1 over g of c. And then I'm going to do, so let me split it up first, and then we'll motivate why the limits all exist. Like that. Okay, so I've got 1 over g of c. Again, I can pull it out, no problem. It's just a scalar. I get 1 over g of x. That exists because, again, g is continuous, right? Again, this one requires a little bit of thinking. G is continuous and g of c is not 0. So by the quotient limit rule, right, we know that 1 over g is also continuous at c, right? Because g of c is not 0. So we really need that condition. And then again, we're using differentiability implies continuity. And then the final thing, hopefully you see that this minus sign, so I just took that minus sign out of the numerator so that instead of g of c minus g of x, I have g of x minus g of c, right? Because we recognize that thing as being the derivative. And so let's just take the minus sign outside. We don't have to worry about it. And yeah, if you put all this together, what do you get? So you're going to get 1 over g of c. This limit evaluates also to 1 over g of c. And then this limit is negative g prime of c. And if you put all that together, that's exactly what we said it would be. So I think, in fact, this is a little bit easier than even the product rule, right? Like magically, everything worked out really, really quickly. Okay. And then in practice, we're never going to use the reciprocal rule. I really just wanted as a theorem to prove the quotient rule. We're just using it as a lemma to say the following. If f and g are differentiable at c and g is not 0, and g of c is not 0, then f over g is differentiable at c. And okay, so like this, hopefully it's evident that this theorem is really just a combination of the product rule and the quotient rule. And so you might even ask, well, why do we even need to state it? Why don't we just, or the product and the reciprocal rule. So why do we even state it? And it's true, you don't have to state it if you don't want to. You can just always keep in mind those two theorems and combine them whenever you think it's appropriate. But the nice thing is that if you actually combine them and you do a little algebra, you get this formula. And this formula is nice. It has a certain amount of symmetry to it, right? In fact, the numerator here almost looks like the product rule, except of course it has a minus sign in it instead of a plus sign, right? So I've got the derivative of one times the other, and then instead of adding them, I'm going to subtract the other term, right? FC, g prime of c. So it makes it fairly easy to remember, because if you remember the product rule, you remember the quotient rule is almost the same, except it's got this minus sign, and then I have to divide by g squared, right? So again, even in my brain to this day, when I do the quotient rule, I do derivative of the first times the second minus the derivative of the second times the first divided by the bottom squared. Or I guess I say derivative of the top times the bottom minus derivative of the bottom times the top divided by the bottom squared. All right, so still to this day, I say that when I use the quotient rule. It's just so heavily ingrained in my brain. Okay, and again, by the product and reciprocal rules, we get the differentiability condition, right? So by the product and reciprocal rule, if we write f over g as f times 1 over g, both functions are differentiable. So 2 is f over g, right? And then now to differentiate them, we're actually just use the product rule with the reciprocal rule. So moreover, f times 1 over g prime. I'm just going to write this one out in, again, kind of like painstaking detail, but hopefully you're like, you know, it just helps you see what's going on here. So derivative of the first times the second. No, just times the second, not times the derivative. Plus the first times the derivative of the second. Okay, and then we're going to use our reciprocal rule to figure out what that is. So that's going to be minus g prime of c f of c all over g of c squared. Oops. Eraser, why aren't you working? Oh, there you go. G of c squared. And then to get our nice formula up there, we're just going to give everything a common denominator. So we're going to multiply the left-hand term by g of c. And of course, that gives us exactly what we wanted. Minus g prime of c f of c g of c squared, like so. Okay. So that's our quotient rule. And then again, as a quick example, let's redo the same example that we did above, but this time with the quotient rule. So example. So let's again find the derivative x squared plus x plus 1 over x squared. This time we use slightly different functions, right? So last time one of our functions was 1 over x squared. This time it's just going to be x squared. All right, so we're going to let f of x be the numerator. And g of x be the denominator. And we know how to differentiate both of these, all right, because they're just polynomials. That's pretty easy. G prime of x is equal to 2x. Now if we apply the quotient rule, so we have the derivative of the top times the bottom. So applying the quotient rule. So we'll get the derivative x squared plus x plus 1. And again, you know, eventually, as you practice this more and more, you get so good at it that you don't even need to like write this step out. You can kind of just do it. But because technically it's our first time doing this, I am actually going to write it out. All right, so what is that going to use? It's going to use 2x plus 1 times x squared minus x squared plus x plus 1 times g prime, which is 2x, all divided by the bottom squared. So that's x to the power 4. And if we simplify this a bit, what do we get? So we get 2x cubed plus x squared minus 2x cubed minus 2x squared minus 2x divided by x to the 4. 2x cubes cancel out, so we get negative x squared minus 2x all divided by x to the 4. That's negative x minus 2 over x cubed. And that's the same answer that we got above, right? And this is kind of one of these nice things is that for any function that I give you, there's actually probably multiple ways of differentiating it, depending on which rules you use, product rule, quotient rule, whatever the case might be. But at the end of the day, as long as you use valid techniques, you'll always get the same answer, right? I think that in this case, this might have actually been a little bit more work. Maybe not, but I think it was a little bit more work than if we had just done the product rule. Yeah, I mean, we also didn't need to know what the derivative of 1 over x squared was, right? We just needed to know the derivative of x squared. And that's really easy, right? The derivative of x squared is way easier than the derivative of 1 over x squared. But yeah, either way, you'll get the right answer, right? As long as you apply the correct techniques and do everything legally, you'll always get the same answer. Okay? And so those are the main kind of computation tools. We now have a bunch of tools for putting things together. So if we know the derivatives of a bunch of functions, we can smush them together using the product rule, the quotient rule, linearity. The reality is we don't have too many functions yet, right? We basically only have rational functions, like polynomial divided by polynomial, and we can now solve all of them. What we're going to do is, like I said, sort of next week, we're going to look at the chain rule, the inverse function theorem. I'll probably also do sine and cosine for you, though, so that at least you have them, right? So you can figure out what the derivatives of sine and cosine are. And then with the quotient rule, you can then figure out all the other ones, secant, cosecant, cotangent, all those things, right? Tangent even. So yeah, that's kind of where we're going and where we'll handle next week. That being said, I'm sure it's not your concern. It's not what you're worried about. Because of course we have the test starting tonight and going into tomorrow. Okay, so that's going to finish this off for today. Everyone keep an eye out for that test. Again, it's going to go live at 9 p.m. It's exactly the same format as term test 1. So, you know, don't worry that something is going to change and there's a curveball there. It's the same sort of thing. I'm going to stay around pretty religiously for the first hour or so. So I'll be around from 9 to 10. And I'll be checking Piazza constantly. So if you have any immediate questions, you can ask. And then tomorrow, Friday, I'll be on and off, right? So I'll have long periods that are on and long periods where I'm not around. So, you know, ask your questions early and ask them often. Don't wait until 8 p.m. Friday, because I make no guarantees, no promises that I will be answering questions on 8 p.m. Friday, right? It'll be fine. What's the worst that could happen? Again, all you need is that if it goes poorly for everyone, right? As long as everyone suffers together, I think it's okay. Yeah, Friday at 9 p.m. Exactly. And don't forget, everyone, you can submit as many times as you like before that deadline, right? So before the deadline hits, you can submit and then you can go back and you can resubmit. What you don't want to do is it comes to like 8 p.m. or something and your internet dies and you're freaking out, right? So if you finish a question, just upload it, right? Don't just take the time, get it uploaded and submit it. And then go back and submit it again when you finish the next question, and then submit it again when you submit the question after that. Like, you can submit as many times as you want. So have it in there and submitted. And then that way, if something does go catastrophically wrong, everyone thinks it won't happen to them until it happens to them. You know, just make sure that you have something up there, because you have 24 hours, right? You really should not be pushing this until 8:55 p.m., right? That is not when you should be uploading your solutions in a 24-hour test. Okay, everyone? So good luck tonight. Like I said, don't hesitate to ask some questions. Today is a very busy teaching day for me, but if you have any last minute questions, again, just throw them on Piazza and I'll try and get around to them before the test begins. And I will be on, test is on CrowdMark, Yeah, Kevin, I don't know, maybe you missed the first test, but it's exactly the same. So there will be a CrowdMark link that will become available as soon as the test goes live. And then if you go into the syllabus, you'll be able to see where the test questions are located. And yeah, that's how it'll go. So it's exactly the same way as the first one, right? Exactly the same way. Okay, thanks everyone. Thanks for coming. Have a good weekend. Good luck on your test. And I will see you next week. Okay, I will see you next Tuesday. Okay, thank you everyone.